Okay, so we're going to be working on this problem here. So we've got these 3 point charges, Q1, Q2, Q3. First, we're going to find the total force on Q1, on Q2 from the other two. So remember, likes repel and opposites attract. So Q1 and 2 are both positive, so they're going to repel each other. So 1 is going to try to push 2 over. 3 and 2 are opposites, because 3 is a negative, so 3 is going to try to pull 2 down. 2 and 3 are just glued in place. They're not allowed to move. So we're going to use the principle of superposition here. We're going to find each force as a vector. That's important, as vectors, and then add them as vectors. So let's find the forces on Q2. First, we're going to do the force of 1 on 2. How much 1 here is pushing on 2? Well, we're going to use Coulomb's law. In magnitude, that force is K, Q1, Q2 over their distance squared. Remember, don't ever put signs in here. This is the magnitude of the force. We figure out the direction by looking at the likes and the opposites. That force is going to point to the left because these are both positive charges. This will never tell you that. Coulomb's law won't tell you which direction the force it will be in. It'll just tell you the magnitude. So we just type in all of our numbers, our 2 different charges. Our distance was 0.3 meters squared, and we get this force here that points to the left. So as a vector, that's this vector. Notice we have a negative x component and a 0 y component. Next, let's find the force from charge 3 on Q2. These are opposites, so Q3 is going to try to pull Q2 down. That's going to be a force down. In magnitude, that's K times the product of the absolute value of the charges. Never stick in negatives into Coulomb's law. We already used the negative. That's how we figured out it was a downward force. But we don't type negatives in here. So K, we'll always just use 9 times 10 to the 9th for K. The 2 charges, their distance was 1 centimeter, 0.1 meters squared. And we get about 1.4 micronewtons. And that's in the downward direction. So as a vector, that vector is 0, negative 1.4 times 10 to the negative 6. Then the net force, we just add those 2 vectors together. Add the first vector with the second vector, add the x's, add the y's. We get this net force on the vector. Notice that points in the negative x and y direction. So Q2 will be drug. That can't be right. Yep, that was right. Q2 will be drug down this way. He was pushed away by Q1 and pulled down by Q3, so he'll come down at some angle like this. So let's find the magnitude and direction of that new vector. So it's down here in quadrant 3. Magnitude of a vector, you guys know that's just Pythagorean, square root of the x squared, or the x component squared plus the y component squared. We get about 3 micronewtons, and we're down at this weird angle. So here, this is my F net. Here's the y component of it. Here's the x component of it. This angle theta here, tangent of theta should be y over x. But remember, you can't trust your calculator when it comes to arctangent. You throw that in your calculator, you do arctangent of the y over the x, and you get 28 degrees. But that's up here. Arctangent always spits out angles in quadrants 1 and 4. Our angle is down here. So either we need to add 180 to that if we want to measure from the positive x-axis, Or we can just measure this angle here. This angle is a 28-degree angle. So the net force has this magnitude, and it's 28 degrees from the negative x-axis, or 208 degrees from the positive x-axis. Okay, now let's find the net force on Q1, on this charge right here. So Q2 is going to try to push our charge away. He's going to try to push him this way. Q1 and Q3 are opposites. He's going to try to pull him that way. Okay, so F2 on 1, we already know that's just the opposite force of 1 on 2. We just did that a minute ago. 2 on 1 will be 2.68 times 10 to the negative 6 to the right. Those are a third law pair. 1 was pushing on 2, so 2 pushes back on 1. So F2 on 1 is this vector, equal and opposite to what 1 on 2 was. For 3 on 1, remember these are opposite charges, so they'll be attracted. Our force will be down at this little angle here. We need to find this distance. So we have to use Pythagorean on this right triangle to get the distance, square root of x squared plus y squared. We get about 0.316 meters. That's in meters. Then the magnitude of that force will be K times the, remember, use positives here, the two different charges divided by the distance squared, and we get this magnitude of the force, and it's down in this direction. We want to figure out this angle here, so we use trig to find that angle. So this right triangle right here was 0.1, 0.3. We'll do an arctangent of 0.1 over 0.3. This is an 18-degree angle. So F3 on 1 points down at an 18-degree angle down this way. Okay, so here's 3 on 1. We need to break that into components. To add vectors, we always have to have components. So I need the y component and the x component of that vector. So I have this right triangle. I know my angle. I know the magnitude. We just found it. So Fy here will be negative. It points down. Magnitude of the vector times sine of the angle. Fx points to the left. So that'll be negative magnitude cosine of the angle. So putting those together, make sure we get our x in the right place. Here's the vector of 3 on 1. Points down like this, negative x and negative y. Then the net vector, the net force on that vector, is the one from 2 and the one from 3. Add them together as vectors. Add the x components, add the y components. We end up with this net force as a vector. To find this magnitude, just Pythagorean, square root of x squared plus y squared. To find the direction, use trig, do an arctangent. We get a 6.6 degree angle right here from the x-axis. Remember, when you're giving direction, you always have to say from something. Okay, so that will be my net direction and force.